Mary University. And in the last year, I've been working on the autonomous control of flying cameras. My PhD was mainly about single camera multi-target tracking and activity analysis. So what I want to do now, I basically want to transfer that knowledge to flying cameras in order to make them autonomous. And in the last year, I've been working on this topic. So what I'm going to present to you today is like a recent work I've been doing. You can find like the details on these publications that I will show you later as well. And so let's start saying that in the past few years, we have been going through an evolution of the cameras. So now we have flying cameras that we can use for recordings. These are a few examples that you can find on the market. And basically, we started with a transmitter that you can use for manually controlling the position of the camera. And now we pass to a GPS-based positioning, which basically with your phone, you can set some desired points of view. So let's say that you want to have the camera in front of you that follows you and records you. So you can set like a position, and the camera will follow you, maintaining the relative distances between you and the camera. What I want to do in my research is to go beyond this and to develop a system that uses multiple cameras. So let's say that we want to do some filming from multiple viewpoints, because, like for instance, we want to select the best view after the recording. And in order to do this, we need to maintain the relative positions from the cameras. So we need to have a formation that follows the object. And also, we need to do some local processing on the top of the cameras, because this one will allow us to reduce the communication cost with our device, will allow us to perform the computer vision or the operation on the top of the camera. And in addition to that, we want to do it distributed in order to make this framework scalable. So let's say that we use 4 cameras, and then we want to expand the system to 12, 20 cameras. We need to be able to do local processing. And also we will be able to do, we will be robust to failures. So if we have a camera that starts failing, the other ones will be able to recover. So what are the challenges in this? We need to have a stable formation. So we need to maintain the relative distances among the cameras. We need to avoid oscillations of the cameras. So we don't want to have jerky recordings. We need to maintain the view on the target. So from the cameras, we want to have the target well-centered in its field of view. And we need to be able to also adapt to motion variations of the target. Okay? So if the target performs some sudden maneuvers, we want to be able to adapt while maintaining the view on the target. So let's start with some definitions. So we have a formation, in this case of 6 cameras. Here we have our target. We define this formation as C. And each camera is characterized by a position in the 3D environment and an attitude, so the orientation of the camera with respect to the global frame. And then we have onboard cameras that in this case are fixed. So we decide to go for fixed cameras because if we have a formation, we don't want to have like big flying cameras. So if we use, for instance, a gimbal, we need a lot of payload, and we might not have it. And then in addition to that, if we have local processing, there will be also the weight of the platform that we are mounting. So the cameras are fixed. And here you can see some examples from the views of the flying cameras of the target. Okay? Then if we are using GPS locations, as I said before, here we have the target. We set some goal locations that the cameras want to reach. So when the target moves, this goal location will move also together with the target. So the goal for the cameras is to reach this goal location that we call as G. And the idea is that we want to have the target fully included in each field of view. So we start with the GPS sensing. So we have the position of the target. We have the position of the flying cameras. We apply some interaction forces, so in order to avoid collisions. So here we have the position of the neighbors in the formation. We have goal forces that are attracting the cameras towards the goal location using the target position, and then we will actuate the quadrotor. So in details, we have our quadrotor. We have the forces that are applied to the propellers. We have the state at k minus 1, at time k minus 1. And the controller takes an input, a desired trajectory point in the next time step, so at k, so what we would like to reach with the quadrotor, and desired first body direction, that is the heading direction of the quadrotor. In this case, I put it in red. So let's say that we want to maintain the quadrotor with this heading direction. So given these two values, the controller will estimate the forces applied to the propeller to move the quadrotor, and the third body direction for the attitude. So in this way, you will have the new position and the new orientation of the quadrotor. So for the heading direction, we can calculate it using the desired position that we want to reach minus the previous state. So now we want to compute this desired direction in order to move the quadrotor. And we will use the neighbor's position plus the target position. So the way we calculate it is, from the previous state, we apply a displacement that is based on our fixed goal locations around the target, and multiplied by a weighting function in order to smooth a little bit the behavior of the cameras to go towards their goal locations, and then some forces. Okay, the distance is the attractive force towards the goal, so how fast we want to reach the goal location, plus some repulsive forces that are used to avoid the collisions among the cameras. So for the simulations, the objective is to maintain the target centered in the field of view. We randomly initialize the starting positions, and we define the goal positions with this formula, which basically defines the shapes like an hexagon, octagon, decagon. And for the particular case I'm going to show you, I'm going to show an hexagon. For the trajectories, I'm going to show you two trajectories, one without direction changes, and one with the direction changes to show you the behavior of the flying cameras. So in the first case, here below you see the view from the flying cameras. And as you can see, there is initialization, is a little bit jerky, but at the end they converge on target. And you can see that the view from the cameras is nice and stable. Of course, the trajectory is pretty easy, but you can see what we would like to achieve. With direction changes, I used a sinusoidal trajectory that shows that continuous variations in the motion direction. And as you can see, the view is really bad. I mean, it keeps moving, and we can't do really much. Okay, and this is only using the GPS locations. Okay. So this is a method that is based on GPS positioning only. It's really robust to follow a target because you have like nice and clear locations to follow the target. It works, of course, when you have the GPS signal available, and especially when the GPS signal is strong. You don't need to have a lot of error to have this method working. So the problem is that we don't have any knowledge about the target inclusions in the field of view of the cameras. Okay? We don't know where the target is. We only know the GPS location of the target. So how do we follow the target without using GPS? Well, let's use smart vision. So let's apply video analytics to the camera that is mounted on board of the flying camera. Of course, this will cause noisy target detections that in turn will generate incorrect control commands. So because if we use the video analytics that are noisy, we will also have noisy controls. And we can run the risk that the target could go outside the field of view. So with the perceived position, with the perceived state of the target, we map the position of the target in a mapping space, and we do some distributed consensus in order to be robust against these problems that are noisy detection. So using the velocities that are estimated from the other cameras, we try to apply some distributed consensus in order to achieve an agreement on the maneuvers to do. And then we will apply some geometric constraints in order to maintain the shape of the formation. And we will actuate the quadrotor plus some delay that will allow us to smooth the behavior of the cameras. So in details, we have the same controller. We want to calculate the desired trajectory point in the next state. And we have the view from the cameras, as before. But now we apply target detection. So, for instance, if we are following a person, we can apply, for instance, a person detector that will tell us where the person is in the image. So we will have the position of the target in the image plane of each camera. And then the idea is, as I said before, that we want to maintain a target centered in each camera plane. So how do we control this? Well, if the target, for instance, is on the top of the image plane, it means that with respect to the flying camera, the target is going further. So we need to accelerate the flying camera in order to get the target back to the center of the camera. Likewise, if the target goes on the left, it means that we need to turn the flying camera in order to have the target centered in the image plane. So each flying camera will adapt the velocity using this rule. And in particular, it will calculate a gain using the position of the target on the image plane of the camera, and then a regularizer. So you have an exponential function that will tell you the gain, and a direction. So for the direction, it's a sort of PD controller. So we use, again, this term here, and if the derivative of this term is greater than 0, we will tweak the velocity of the quadrotor, because it means that the target is moving further from the center. Okay, so if this gain increases, it means that we need to do something with the camera. We need to adapt the velocity. So we will adapt the velocity in this way. And then there will be an amplifier that will allow us to give a bit more push. If the derivative of the gain, basically, is not greater than 0, it means that the velocity is enough to maintain the target in the center of the image plane. Okay? So we do this for each camera. The problem is that if we have target detections, this will be really noisy. So we might have different velocities that are applied to each quadrotor. So what we do, we apply here the distributed consensus. Okay? So what is a distributed consensus? Let's say that each flying camera calculates a velocity and shares this velocity via communication with the neighboring flying cameras. Okay? And it keeps sharing, and it starts doing the average, also with the velocity that it receives from the neighbors. And this one is an iterative algorithm. Usually, you can achieve like agreement with the velocity around like 5 or 6 iterations. And then you will have the velocity of the formation that will be pretty much similar, okay? And robust to noise. But we noticed that this one is not really sufficient to maintain the formation of the flying cameras because we didn't apply any geometric constraints to the formation in order to maintain what we wanted at the beginning, like the hexagon. So what we decided to do is to apply a formation algorithm that is called the circle intersection rule that will allow us to impose some geometric constraints on this formation. So to do this, we propose a candidate desired trajectory that we want to achieve, that we call it in this way, and by using the velocity that we calculated with the distributed consensus, okay? So we propose a desired trajectory. Then we will build these two circles around the two neighbors with respect to this camera using the relative position. So we are assuming that this camera can sense the relative position of this camera, okay? So this one knows pretty much where these two are. We build these circles, and we extract the argmin of this function, that is simply the intersection of these two circles closest to this quadrotor. So we have these two terms, and we choose the next desired location based on a tolerance term, okay? This tolerance term is determined using this formula. So this one is the distance between these two quadrotors that have been measured, and this one is the desired that was set at the beginning of the algorithm, okay? So if this distance is less than a certain tolerance, I apply the desired trajectory point determined with the distributed consensus. Otherwise, I will use the circle intersection rule to decide the next state. And this one will allow us to maintain the geometric shape of the formation. So for the simulation, we will evaluate it using the ratio of the cameras that are viewing the moving target, calculated as the number of cameras viewing the target divided by the total number of the cameras in the formation. So for instance, if there is a formation of 10 cameras and only 6 are viewing the target, this value will be 0.6. And we use the same shape for the formation. And now I will show you the results on this trajectory. So in this case, without using the GPS, by using only the vision, we can still follow the target, but the cameras will understand that this target is actually going in this main direction, and these ones are only little movements that they don't need to be addressed like the movement before, because we have this mapping function that is smoothing the movement of the target. And the cameras will keep following the target. So here we have another trajectory. It's better if I make it quicker. So in here, you see that there are little variations of the target, but the camera are still following the target properly. And then, when the target will start turning, the cameras will start following it because they perceive this movement like as a turn of the target, but not as noise as it was before. So they will keep track of the target, and here you can see from the views that you still have some views that are nice with the target in the center of the image plane. So for instance, if we want to choose a view later on that we prefer, we can say, okay, this one because the target was nicely in the center of the trajectory.
So
yeah.
you assume the target moves slower than the UAVs, or the flying?
I used some velocities that are like a person running. So yeah, in that case, yes. So the flying cameras can go much faster than the target, yes. So here I put some results, some numerical results, where I evaluated the ratio of the flying cameras that are viewing the target. And of course, we would like to ideally maintain always one, so it means that the target is always inside the field of view of the cameras. But as you can see in this trajectory, we have this drop, okay, of the viewing, where it goes at almost 40%. And what happens here is basically that during this turn, the camera, they take some time to go on the target. So the target is a little bit farther with respect to the center of all the cameras. So that's why you have that those performance. And in this case, we have like little problems, and it's because of this movement that some of the cameras are losing the target, and the target goes outside some of the fields of view. So in this case, we tested the algorithm by modeling some inaccurate target position and some misdetections. So we are simulating basically that the detector that is on board is making some mistakes. Sometimes it gives a wrong location of the target, and sometimes it misses the target completely. So in here, there is the noise in terms of position noise of the target that increases. And here you have always the ratio, the average ratio of the flying cameras that are viewing the target. So as you can see here, when the position noise increases, the ratio of the flying cameras viewing the target decreases as well. But still, we can maintain like 50% of the cameras viewing the target, even if we have this type of noise. And in here, I modeled the misdetections, where in this case, it means that this is the 50% of the times that a flying camera misses a target, so it doesn't detect the target. But we can see that in here, even with the 50%, we have the 30% of the cameras that we can still see the target. So it means that the distributed algorithm is really important to make the system more robust and to avoid incorrect control commands, basically. Yeah.
And the first one, I find it slightly counterintuitive that you've got a big drop.
Here you can find all the details about the implementation. And this is the end.
Yeah. Do you also filming each other as well?
Sorry?